Welcome to Lattix version 12 webinar. What you're looking at now is the DSM, dependency structure matrix. This is hopefully familiar to most of you who've maybe used or seen Lattix in the past. By way of a quick reminder, this is our example project that we often use to show Lattix with. And you can see just a quick recap on a DSM there. For example, we have the COM component of our ISO-glib example. Reading down the columns tells us what a component is using, and reading across a component tells us what a component is used by. And in general, a good architecture generally tends to be a lower triangular system where most of the dependencies are below the diagonal. And so Lattix, as you will already know, offers partitioning, which enables you to sort the system by usage. And that groups the components that are used heavily at the bottom, and the components that are using those components tend to be grouped towards the top of the application. You'll also remember that Lattix has the ability to enforce rules, and there are three different types of rules. There's layering rules, which determine the desired ordering of the components. So, for example, COM sitting at the top, scheduler, driver, HAL, and util may be our preferred layering. And there's also independent subsystem rules. So these components that you see inside the COM layer should be independent of each other. And we've set those to be independent because that's a design feature of this system. And then that can be enforced so that if I, as a developer, come along and create a bad dependency between two components which should be independent of one another, then I will get a notification that I've violated the architecture. And then the third type of rule is API level. You can go right down to the member level, and we'll do that a little bit later, and measure and monitor the impact of a change to an API on the whole system. So the red options here are where there are rule violations, and the relationships above the diagonal tend to be the ones that we're concerned about and interested in. So since version 12 has come out, we have implemented some new features around heat mapping. And you can see this new menu up here allows us to view the system by heat map. So I can select here the heat map grid for the entire DSM. And you can see now that the typical things that you as a developer or quality manager would be concerned about are now visualized in the context of the architecture. So, for example, as we're testing maybe a functional safety project, code coverage is of interest. We often have a requirement for, say, 100% code coverage if we're doing ISO 26262 software development for the automotive standard, or FDA for the medical devices industry, or 61508 for general industry. All of those standards measure code coverage. And so now, at a glance, we have the ability to import coverage data from tools such as Cantata. And indeed, there's an entire Cantata menu option here to assist you and assist Cantata users to generate projects directly from the code in the DSM. But for the moment, we're just viewing the code coverage through the prism of the architecture. And we can see where, for example, we haven't achieved sufficient entry point coverage, decision coverage, or statement coverage. So that gives us this view here. We can set the thresholds now as well for what is passing and what is failing. So we're using a traffic light system. Red is code areas or code areas which are of particular concern that aren't within our threshold. Orange is maybe at the warning level, and green is obviously accepted within those thresholds. So I have complete freedom of autonomy to configure the coverage thresholds here, and so I've set 80% as warning and 50% to be failing. I can also visualize static analysis defects. So, for example, we have an integration and a module with Axivion, which is a world-leading static analysis tool that offers coverage of the AutoZAR and MISRA standard. 94% of all AutoZAR rules are covered by the Axivion tool. And so now we have also the ability to visualize those defects inside the components. And as I expand, you can see your eye is drawn to those areas where, for example, we haven't achieved the entry point coverage threshold, and overall our violation count has been exceeded. And this violation count is a composite number comprising the coverage data, the AutoZAR violations, MISRA violations if you're measuring those, and you can see the breakdown per file of all of these violations. So that gives management an easy way to see, or project leadership, easy way to see at a glance where the technical debt is in the system, where we need to put some remediation effort, where we need to focus our work in the next sprint, for example. And indeed, you can actually link this data as well to other tools in the ecosystem, such as Jira or GitLab, and then go on to create issues once you've decided what to do based on this data. So the other grid options are visualizing the DSM information by system stability, and that switches on a different view. So again, green is obviously code which is stable, and by stability we refer to the Lattix metrics which are available. So system, architecture, and object-oriented metrics are all available, and you can see we have a low system stability value here. Just as a reminder, this is a measure of how sensitive the architecture is to changes within a subsystem. Another way of expressing this is this particular system is sensitive to changes. In fact, you could run what we call an impact report on a component that's changed. And if you expand this, for example, and let's say you're changing a header file, but you want to know what kind of impact that has on my system, I could mark this as changed. And by the way, this change could come from a Git commit as well. So it could be an event stimulated by a check-in, for example. And then you would run an impact report on that changed component and calculate the transitive closure of the change. So that means calculate every possible effect on the whole system by changing this component. And what you see is, changing a file down at that level actually creates 7, you could call them ripple effects through the system. So touching the file changes all of these things, and changes all of these things, and so on and so forth until you get to level 7, where the entirety of that change is then computed. That can then be exported into a pipeline, a DevOps pipeline, and passed to what we call smart test. And that addresses a particular problem in the industry where, as the code is getting more complex, code complexity goes up, the number of test cases we need goes up. And so it takes longer and longer to run every test. And before long, even for medium complex code, it takes too long to run every test, or it's infeasible to run every test with every change. So our smart test, which is based on the integration with a unit testing tool like Tata, actually passes the data to Cantata to enable Cantata to trigger the correct unit tests. And that greatly minimizes the amount of retesting that we need to do with every commit, because we're only testing the areas which have actually changed. So that's our stability view, and you can see there are many files which are unstable, and so we can prioritize our efforts on stability. We can also view the individual coverage heat maps. So for example, we can see where we haven't achieved sufficient decision coverage, the same for statement and entry coverage. And as I say, we have the integration there with AutoZAR, and here with the Axivion tool, here we're measuring the AutoZAR violations across the system and setting thresholds on this ISO glib component. And there's no surprise that actually we have mostly red, because this particular library wasn't built with safety in mind. It's not a safety critical software development. So most of this is actually red, as you can see. And then for any of the violations and defects, you can actually see which AutoZAR rules are being violated by which component. So For example, Rule 1903 A1601 talks about conditional compilation for include guards, and you can actually see the listing and the violation down to the lines of code. So the Axivion module that has just been added to 1203. You can actually now load data directly from Axivion analyses, and the advantage of doing that is Axivion uses the EDG parser, EDG front end from Edison Design Group. That contains a huge number of dependencies. So maybe if we could just do Control D on this screen, Frank, if you're around and helping, we can actually see the extensive list of dependencies coming from an EDG front end via the Axivion parser. And this gives us a richness to the data, which previously through CLang provides a certain amount of information, but this goes over and above that. And now we have more detailed dependencies that we're actually visualizing in the DSM through the Axivion module. Axivion also is closer to the build, so it does an analysis of the build system and intelligently computes the defines and includes. So you get a much closer, because you're closer to the build, you get a higher level of accuracy in using this module as well. And for the very first time, because of Axivion support for C#, you can actually visualize dependencies between C++ and C# components, which is unique in the industry. Across those interfaces between .NET and C# and C++ code, those dependencies can now be visualized. So that's the summary of the heat maps, and the measurement violations can also be visualized if they're switched on, which they're not for this because it's a C++ project. Let's talk now about security and the partnership that has been started between Lattix and Whitesource. So Whitesource, if we could look at the Whitesource dashboard, is an open source analyzer. It's a C, C++, Java, C# supported platform, and it analyzes all these code bases with respect to three characteristics. And the first is security. So are you using open source components which have security vulnerabilities? The second usage is license usage. So from a compliance perspective, are we using licensing such as GPL or LGPL, which impose certain obligations on us? Or are we using permissive licenses such as MIT or BSD, which are more allowed? And then the third aspect of open source risk management tends to be operational risk. Operational risk would look at, for example, data such as how many contributors does the project have? Am I at risk because of a component that's in the center of my architecture with maybe one contributor? And so what happens if that contributor stopped working? Is my system at risk? And so bringing in the open source analysis data from Whitesource, but viewed through the prism of architecture, for the first time, we believe, enables us to evaluate the effectiveness of open source and also the impact of changing, removing, adding, subtracting an open source component from the architecture. So here's an example. We have analyzed a system called CLAM AV. And if I just scroll down here in the browser, you can see there's a list of libraries that are being used by this application. And you can also see that there's some license risk and some vulnerabilities there. So I have two security vulnerabilities, and these are called CVE vulnerabilities. So CVEs are the common weakness and vulnerability listings, and those are present in these libraries here. And so if I click back to Lattix, what you'll see now is we can import this data and now visualize where the CVEs are occurring inside the DSM. And so, as again with the heat map, we can view by particular CVE, or the consolidated view of everything shows us that we have the stability issues here, the CVE issues are here in this column. And so I can scroll down and actually just view that CVE in the heat map here. And actually, also now what I can do, I can see that the CVE data is, the violation is in this component. This data has now been imported by Lattix from using the Whitesource API, and now I can see which files are vulnerable to this CVE. But the bigger question is, well, you know, what's the impact of changing this component or the impact of this CVE on the system? Is it a component that's being used in unit testing, which maybe is not going to be in my release, or is it central to my architecture? So exactly as we did with the MISRA and the AutoZAR violations, we can now perform an impact analysis based on the CVE. So I'm going to run a report now on impact, and you can see here I can choose the CVE tag for this this high priority vulnerability that Whitesource has found, and I can measure the impact of this vulnerability to transitive closure and decide based on that. Again, I have 7 levels of impact that this CVE has on my system, because this component here, this lib clam, is being used by all of these things in libclam. And then if I go to the second level, I see all of these things are used by all of these things, until eventually I spring out of that component and up to the common layer, and then into my ISO, into my project. So you can see now that this vulnerability is concerning. We have a CVE identified. We have a piece of open source that is critical in our architecture, and therefore we can now determine to address that. Again, if I select the metrics thresholds here, I can set my CVEs. So if you have a security policy or taxonomy whereby you're allowing certain CVEs or tolerance to some CVEs, you can set those thresholds in the DSM to pass or fail, and give you, at a glance, at a couple of moments, the visibility that you need to where all of this is coming in and affecting. So this is kind of a new way of working. Lattix is really becoming a central source of truth now, not just for architectural data, but also for open source clearing, for security, for code coverage. You can also import tests, unit test data from tools such as Cantata, so that you can visualize, for example, which parts of the components are failing your unit test and maybe need more unit testing to be done. So all of those filters exist. And again, if I go back to the dependency listing with Control D, I can actually now filter and just reduce, for example, the DSM to look at global data. So if I selected all of the relationship types which concern themselves with global data, then that will give me the visibility of the global data usage in between packages. And this is of particular interest for data coupling and control coupling coverage, which is a requirement of the avionics standard. DO178C requires this. There's a couple of ISO 26262 projects which also need to prove that data coupling is not occurring. And so the first step of data coupling coverage is to visualize where those data writes and data reads are occurring. And you can see exactly to the line number where global data has been written and modified. You could then pass that to your unit testing tool. In fact, there is an integration to do just that, to create the Cantata project data from the selection, and then you're well on your way to creating your control coupling and data coupling verification project for your unit tests. Just while I'm on the Cantata menu, there's a couple of other options there where you can actually create projects from a tag. So you could tag a group of components, for example, as being part of the same integration unit, and then run a script there to create the resultant Cantata, the Cantata project. So filtered on global data, we focus on the data which crosses the module boundaries, and that's all of those represented in this DSM here. And if I just undo that and put back all of the other dependencies in the DSM, and go back to the top level, I can just restore the defaults here, and then I'm back to my view that I had at the beginning with all the dependencies, and scrolling back up to the top of the DSM there. Let's just come back to the top level view here. Then we now have the impact analysis. We've done the heat mapping, and we've looked at the impact of CVEs on the system. So Test Architect also has a test prioritization option and change-based testing via tags. And again, that is best used in our experience in a pipeline. So perhaps we could switch to a pipeline view on the slide, and then we can explain how this integrates into a DevOps pipeline. What we have noticed is if you use architectural data in the correct way, the architecture can improve both the build and the testing phases. So we've already looked at the testing side. We call this approach smart test. If we now use architectural data to look at how we can improve the build, you'll see from the DSM, if we just one moment go back to the DSM and look at the squares which are independent. So we have a lot of information is contained and conveyed in the DSM cells, and each cell conveys design intent. What we also see, where there's no relationships between components, there's no dependencies between those components, these are independent subsystems. And so for those of you who need to build faster, maybe you have the problem of a long build time, or you have a brittle build, or your build is somehow unreliable, and you'd like to improve that build, then using this data to see which parts of your system are codependent and independent of each other allows you to do something what we call smart build. So if you go back to the slide, smart build can take this independence data, and for example, you see on the first pipeline step there is the build step. The build is really the most important part of the software system. If our build is brittle, our testing phase is often brittle because we need to build the software to do the testing phase. The release is suspect. Often, if developers are scared to change a particular area of code because they're worried about affecting the build, that is itself an expression of technical debt. And so what you see here is a parallelized version of the build step, and that is because we use Lattix data to identify which subsystems were independent of one another. Therefore, they could be parallelized, and we can even write the Jenkins pipeline script that builds those components directly from the DSM. So this is our early work into something called Smart Build. And if you're struggling with any aspect of your software build, but particularly build speed, then what we can do is do a DSM analysis of your architecture, look at which components could be identified as buildable faster. And then, for example, you could use something like Conan. If you're doing a C++ development, Conan from JFrog Artifactory is a C++ repository and package management system. And so you could change the way you're building from compiling all the time to consuming pre-built packages. And we've undertaken that work with a couple of customers with some success to help Conanize, just to help build the software faster. And people that do that often report that what you're seeing here is a null release. So this is everything I need to do if a line of code changes. The null release does actually get a lot faster if you use package management like Conan, and also the smart build approach, where you actually identify which components can be built independently and then execute that in a DevOps pipeline. So we have had some good results with some folks reporting build times reduced by 50%. In one case, we had over 2-hour build reduced down to 40 minutes, which was an excellent result, and actually changed the culture of the way software was being built. The null release, as I say, everything you need to do if you change one line of code, that's what you're seeing now. I need to rebuild, I need to retest, I need to revalidate, I need to check there's no security vulnerabilities, and then I publish all this data to SonarQube. So V12 has APIs into SonarQube. You've seen the connectors to Whitesource, you've seen the connectors to Cantata via Test Architect, and now the connectors to the build system itself via Jenkins. We also have a partnership established with GitLab, and these pipelines are available in the GitLab CI system. So for those GitLab users, these pipeline steps are fully automated and integrated as GitLab pipeline steps into the GitLab CI system. We could also do other systems on demand and looking at GitHub Bitbucket. So this is how we see architecture analysis inside CI, inside continuous integration. It's a data-driven approach. The data from each step is used to inform the next step. So typically, we would run this on an architecture which allows the sharing of data between pipeline steps. Typically, that would be a system such as Kubernetes, which has the concept of a shared workspace. And so this system does actually deploy over Docker. There exist Docker containers for each of these steps, which can then obviously be deployed as a Docker stack. And then that Docker containerized system would then deploy on a Kubernetes cluster. And so this scales to the cloud. For those of you who are interested in moving your building and testing and deployment to the cloud, this architecture and this system already exists. And Lattix partners are available to help with the services work if you need any help actually deploying these pipelines and getting this infrastructure running. If you have that vision to go to the cloud, for example, then the expertise is there in the team to do this.